Based on our experiences with derivatives, slopes, and linear approximation, we can now tie some things together and come up with another important concept. So I have this picture drawn here. Well, it was already drawn and I've kind of labeled it. So we have our starter point, a f of a, and then we build a linear approximation, right, a tangent line, based off of that value. Okay, now what we're using is that tangent line to approximate a value that is close to our particular one. So we have the actual point up here. So this is the actual point, right? And then we actually have our approximation down there, right there, right? So there's the approximation. So from the approximation to the actual point, there is an error in between the two. So that's the error right there. Okay, now how do we get this? Well, the change in x, that's also known as x minus a, right? And then what we're using is the fact that, hey, I'm going to go over delta x. In other words, I'm going to have a run of delta x. So I have to have a rise of whatever the derivative of that line is. So to get from here to here, to get to that point right there, that approximation, then I would use the change in x and then multiply it by the slope of that line, right? So the linear approximation has a slope. It's a tangent line with slope, which is f prime of a, which we all know is dy over dx at x equals a. It's a derivative, in other words. So it's f prime of a. So I'm using that slope to get me from this point over to this point. Now that's not actually the same as the actual point. The actual point's up here. So that's change in y. So the change in actual y's is from this actual point down to that starter point. That's change in y. And what we see is that these two, the change in y, the actual change in y, and then this approximate change in y, right? So this is the approximate, and this is the actual change in y. They're very close to each other. Right? They're very similar. They just have a little bit of error. And you can imagine if I slide this point over, if I make the delta x smaller, then that change in y would get smaller and smaller as well because the curve and the line are getting closer and closer to each other. And that leads us to what we would say about delta y, which is this value right here, as delta x gets small. So I would say as delta x gets small, in other words, delta x goes to 0, right, gets small. Oops, that should be two words. Two words, gets small, gets small. There we go. Two things are happening. We can say that the delta y and the delta x are approaching each other. So we would say that delta y and delta x are getting very similar. So the easy way mathematically to say that they're getting closer to each other as delta x gets small is that the delta y minus the delta x, in other words, that change, which is the error, is going to 0. Right? That's the second thing I would say. So the error is going to 0. Okay. That leads us to one more conclusion, which is that as delta x gets small, so not only is this error, right, that difference between these two values, which is that little bitty error, so that orange one minus that green one is going to 0. Then we can also say that the change in y divided by the change in x. Now think about what that would be. Change in y over change in x. So change in y over change in x, it's the slope of a secant line on that curve. Because here's the change in y, here's the change in x. So up that. So this is the slope of the secant line from f of a to x f of x, right, from one point to another, right, from the starter point, from the starter to the actual point on the curve, right? That's what this is, right? So the delta y over delta x is getting closer and closer to, well, look. So there's the secant line right there. There's the tangent line. If I let those points get closer and closer together, if I let this delta x get smaller and smaller, that's going to pull this point in and that point in. So they're going to come into the left. And the slope of that black curve right here, which is f of x, and the slope of that line are going to be very similar, i.e. the same. So it's going to approach dy over dx, which is the slope of the tangent line, which is what L of x is, the linear approximation line. And that's very, very powerful. And that leads us to our next definition box. So right here, we would say that the linear approximation, right, f of x is approximately L of x, which is equal to, right, y equals L of x, which is equal to f of a plus f prime of a times x minus a. So this is the linear approximation idea, so that's the summary of that. And then to approximate the change in y, right, that vertical change we're seeing in the dependent variable, when the independent variable changes from a to a plus delta x, which is a weird way of saying delta x, in other words, delta x equals x minus a. Right? That's what they're saying. So it's just weird to say it. But what does that look like? Well, it looks like delta y is roughly f prime of a times delta x. Right? In other words, here, I'll bring it back. These two are very similar to each other. As delta x gets smaller and smaller, they would get more similar to each other. Matter of fact, vanishingly similar to each other, and that's what this is saying. All right, so let's use that fact and that feature to do a story problem. So, oh, and for more on the importance of linear approximation, because it is truly important. There's a whole NOVA about it, believe it or not, because there are so many formulas in real life that for various reasons we can't work with them directly, so we work with linear approximations to them. And this whole PBS series has interesting bits about it, so feel free to type in that bit.ly link and go watch it. Okay, so we want to approximate the change in the surface area of a spherical ball of ice as it melts from a radius of 4 centimeters to a radius of 3.9 centimeters. Don't forget that the surface area of a sphere is 4 pi r squared. All right, so you can hear what it says. It says approximate the change in the surface area. So we're looking for a change in S. Approximate the change in the surface area. So we're looking for the change in S. As it melts from a radius of 4 centimeters, so that's our starter. Oops, wrong color. Right there. That's our starter. Starting point would be A equals 4 centimeters. Right? Well, it'll be R equals A, right? So R equals 4 centimeters, which is our A value, right? Our constant that we're set up. And we're going to a radius of 3.9 centimeters, right? Right here. I'm just going to note it at this point. All right, so I have a sphere drawn for us. So the radius, of course, to start with is 4, but it's going to be shrinking. That's the whole point of the sphere, because it's melting. All right, so now we have a formula for S. S of R is equal to 4 pi r squared. And we want to come up with a linear approximation that's similar to this. Well, not really a linear approximation, but we're going to use linear approximation to guess what delta S is. So we're going to use this bit right here. Delta S is approximately, so let's make a note. So note, delta S is approximately, right, S prime of A times delta R. So our variables are S and R. R is our X, and then S, surface area, is our dependent variable. Right? A lot of times it pays to figure that out at some point. So if that's the case, right, S is our Y, so we'd say change in S is change in Y, and then we would say that's S prime of A times delta R. So I have my S function, I need my S prime. So S prime of R would be 8 pi R. So I need S prime of A. S prime of A would be equal to S prime of 4, which would be 8 pi times 4, which would be 32 pi. So there's that. All I need now is my delta R, and I'm golden, right? So this would be, actually, I shouldn't really put note here. This is actually the problem. This part over here. This is actually the work on the side. Work on the side. And this is the actual problem part going over here. Okay, so I now know I want 32 pi for that beginning part. All I have to do is figure out delta R, and I'll be set. So let's go over here and figure out delta R. So delta R is going to be the change in R, the change in the radius. Well, let's think here. I went from a starting R, which was 4 centimeters. I have an ending R, which is 3.9 centimeters. So my change in R is the difference between those two. Right, so remember it's X minus A, which in our case would be R minus A. Okay, because R is Rx for this problem. So that would be 3.9 take away A, which was 4, right? That was the constant starting point. And that means that we have negative 0.1 as our delta R. So that's what I'm going to put in over here. Oops, negative 0.1 so you can see it. There we go. Just managed to fit it on there. Right, so there's my S prime of A, and there's my delta R. Right, and don't forget it goes X minus A. Or delta X is X minus A, so delta R is R minus A. And A was our constant value at the starting point. All right, so this would be negative 3.2 pi. And then the units would be centimeters squared because it's surface area. And we're done. And if we want a decimal approximation for that, we could find one, but it's not necessary.